first thank you the organizers for such a beautiful event where we can share our ideas and discuss the corresponding issues, right? So, well, in my today's presentation, I will try to focus your attention on the structural analysis of hyperbranched polymers by means of molecular hydrodynamics in this very crazy composition, right? And we will discuss an absolute macromolecular characteristics, whatever it means, and we'll try to standardize the complete family probably of the branched polymer topologies using the concept of the hydrodynamic invariance and concept of the hydrodynamic homology, and we'll ask whether in general the hyperbranch or the branch topologies can be considered as homologies to each other, right? So once again, we are speaking about hyperbranched polymers that are, well, belongs to the family of dendritic polymers, one of the most known examples of which are dendrimers, which are, well, having the highest level of branching asymmetry. And, well, in contrast to dendrimers, the hyperbranched are regularly branched polymer systems. And in this case, we will also have a combination of linear, terminal, and dendritic units randomly distributed along the macromolecule. Well, yes, and the overall statistical nature of the branching process. However, in comparison to the for the dendrimers, the hyperbranched macromolecules still show the very compact globular-like shapes in solution, small hydrodynamic sizes, and they do as well show large numbers of functionalizable end groups. Like in this case, we have hyperbranched polyglycerols, which are as an end groups having huge amounts of the hydroxyl groups, which can be easily functionalizable, right? And then also in this case, it is water-soluble polymer, which shows also excellent compatibility. And those macromolecules are considered as well, not considered, are very potential as a drug delivery devices, So in this case, in our case, what we have in hand is two sets of samples, the hyperbranched polyglycerols and hyperbranched polyethylene glycols. It's actually copolymers, polyethylene glycol, polymerized for the glycerol as a branching agent. And also, in comparison to dendrimers, the hyperbranch are much easier to synthesize. However, on the other side, due to the statistical nature of the polymerization process, the dispersity is rather high. At the same time, nowadays, such techniques like hollow monomer addition technique or multi-branching ring opening polymerization techniques will allow to certain degree to decrease the polydispersity of the synthesized macromolecules. So and those polymer systems were synthesized in wide range of the molar masses, well, approximately from 1,000 to 2 million in one case, and in another case from around 3,000 to 1 million or to 800,000. So what are the basic objectives of the study? And those, well, fundamentally, of course, we are trying to answer or trying to establish this structure property relationships between the chemical structure of the macromolecule and its corresponding macromolecular behavior in solution and overall functionality. So in this case, when we can predict how the macromolecule will behave and what impact it will have on the functionality, we'll be able to create then the macromolecules with precise properties. Yeah, this is the very general and basic strategy. And meanwhile, of course, we will try to answer or discuss such issues like structural and hydrodynamic homology of such polymer systems, whether they can in general be considered as homologies. And all these discussions, of course, will be accompanied by the corresponding estimations of the macromolecular conformations or establishment or yes, of the macromolecular conformations and the absolute molar masses and other hydrodynamic and macromolecular characteristics in solution that dictate functionality of the macromolecules at certain conditions. So, and well, we use in this case this very classical hydrodynamic approach on which actually the classical problem physics is based on. So we chose a combination of mutually reinforcing hydrodynamic techniques such as analytical ultracentrifugation, intrinsic viscosity or viscosity and density measurements, and also perfusion measurements, either, for example, by dynamic light scattering or some more fundamental isothermal perfusion measurements, or, for example, and also or by yes, and accompanied, for example, also by static light scattering. Crash measurements are also coupled to the ACC, for example, yeah? And already each of the techniques alone provides you rich data set concerning the molecular behavior and the conformation, probably sizes or molar mass concerning your object, but only when you combine all these techniques together, then you can go really deep into the details and literally extract all the information possible on the conformation, on the dispersity, on the size and size distribution, absolute molar masses, shape and hydration, and the composition of your system. Yeah, all based on the very classical hydrodynamic approaches. So, and this is what we're going to do. And first of all, when you speak about the solution properties, you think of probably some viscosity measurements. It is correct, and in this case, we operate with the so-called intrinsic viscosity. Why is it intrinsic? Well, because it is related to the properties of the individual macromolecules, and in this case, it is related to the volume and the molar mass of the macromolecule. And also, it is also related to the volume. It is also related to the partial specific volume and the hydration. Yeah, in the limiting case of the hard spheres, we have this Einstein equation for the intrinsic viscosity, 2.5 for the partial specific volume. Over here, we also have a simple function or the shape function, which can be used to estimate the model parameters your yes of the studied object. And for example, it is known and expected that when you study tendromers and have a set of values of the intrinsic viscosity, and you vary the molar mass or the generation number, you will have, or it is expected to have, a maximum in such a double logarithmic dependence of the intrinsic viscosity of the molar mass. The same dependence actually was also proposed for the hyperbranched polymers, but so far experimental results do not confirm such compositions, I would say. And later I will show you results that we obtained over here. So and over here on this slide, how you can see just a summary of the intrinsic viscosity measurements, the Huygens extrapolation procedures over the concentration. So what you can see that, well, when preliminary molar mass range of these samples from 3,000 to 800,000, and we can see the average values of the intrinsic viscosity is very small, around 5 centimeter cubic per grams, right? And also in this case, if you look more deeply into the details, you see that, for example, the Huygens and the Kramer constants are also, well, abnormally high, I would say, yeah, because, well, in general, they can be used, those constants can be used to, well, in the first approximation to judge about the column quality in the thermodynamic sense, yes, and for polymers and thermodynamically good solvents, one should expect values around probably 0.3 to 0.5, probably to 0.8, and it has a general density to increase for the more pure solvents. But in this case, such high values of the Huygens constant or viscometric constants are related to the compact globular or macromolecular conformations. Yeah, approaching the spherical limit. As far as I remember, it should be around probably 2.4 or 2.6. I don't remember exactly. And also, the Kramer dependence has a positive slope. It's instead of having a negative slope in this case. So similar behavior we also observed for the hyperbranched polyethylene glycols. So, and another important solution property which we also need to discuss is the partial specific volume, which is also one part of the intrinsic viscosity. Yeah, more specifically, well, partial specific volume represents the change of a volume of a system upon an addition of a mass unity, yeah, for the system, and it is a thermodynamically defined parameter, right? And in the first approximation, it can be considered as the reciprocal to the density, yeah. And it is also considered that for homologies, you should not observe any change of the partial specific volume, so it should stay constant. And this is, for example, what we observe for the hyperbranched polyglycerols, whether in case of hyperbranched polyethylene glycol copolymers, we see a variation of the partial specific volume, which can be actually, which was related to the variation in the glycidol content, which was used as the parenching agent and the copolymer actually, and during the polymerization reaction. And well, in order to get more, in order to get information about the molecular distribution, we applied, well, analytical ultracentrifugation, more specifically sedimentation velocity, which basically shows you evolution of the concentration profiles in time upon the applied centrifugal force, which actually and defined at the sedimentation coefficient. The velocity happens centrifugal force, and then it can be related to the molar mass and size the hydrodynamic size of the macromolecules. Yeah? All this sedimentation process is described by the fundamental Lamb equation, which consists of two parts, or the diffusion part and the sedimentation part. So in all the cases, we have two processes, the diffusion and the sedimentation. The Lamb equation is the partially differential equation, which means that it can be solved numerically. Yeah, and nowadays, using the computational power, we can effectively solve this equation numerically, thereby having information on both on the sedimentation and diffusion coefficient from one experiment. And the diffusion coefficient in this case is represented in terms of the friction ratio, very popular construct in the biophysical array, which is related to the shape parameters and the hydration. For the analysis of the sedimentation velocity data, we used different models. I would say the CS model, which assumes, which is intrinsically confined within the spherical model, and the model 3CS as of a sphere, which gives you a distribution of the diffusion coefficient in contrast to the initial CS model, which only gives you an average diffusion coefficient of all the species in the solution. And over here, you can see different solutions of the Lamb equation, which actually equally good represent the present set of the sedimentation profiles. So numerically, we have the same systematic error in both cases. So these distributions are equally possible in both cases. And we see that the average sedimentation coefficients are the same. Yeah. And if you look more deeply on the typical sedimentation profiles, that on the figure R, we see that it must be a very low molar mass sample, having an average sedimentation coefficient around 0.5, and the corresponding sedimentation profiles are very elongated. Well, with increasing molar mass, on the figure B, we have a T-modal distribution, and we see a separate sedimentation profile for each of the fractions. So they are physically presented in the solution, and then with increasing molar mass, the viscosity of the system is also increasing, no matter that it was synthesized under well-defined conditions, right? And at the highest molar mass, then you have a rather broad distribution without any specific peaks like on previous examples. And just to look more deeply probably on the evolution of the distributions of the sedimentation coefficient with increasing of the molar mass, we see the semi-logarithmic scale. So it's increasing, and the polydispersity is also increasing quite drastically for the molar mass. In some cases, we have a primordial distribution. So then I have got information about the intrinsic viscosity and the sedimentation. Then, of course, we also studied diffusion properties. And diffusion, the translation diffusion on the one side, we're estimating using these very classical isothermal diffusion measurements, which can be compared or confirmed in the AC or stationary. But in any case, you will end up with the so-called dispersion of the diffusion boundary. So you make a boundary of the solution and solvent and observe how fast this boundary is spreading in time. And then if you basically plot this dispersion over the time, the slope of the corresponding dependence will give you the diffusion coefficient. And also, in addition to that, the diffusion coefficients were also determined using classical approaches such as dynamic light scattering. So after all, we have such a rather large data set of the diffusion coefficients, and some of them, of the techniques, can be called absolute or independent, and they still give you a different values of the diffusion coefficients. And I will go a bit more deep into the details later. And on the other side, so these diffusion coefficients were then later used to calculate the molar masses using the sedimentation coefficient. And also, independently, we also applied static light scattering experiments. On the one hand, using SEC modes, on the other hand, also at stationary conditions, I would say, yeah, catch SLS. And then we end up at this molar mass matrix, And if you look here, the first 1, 2, 3, 4, 5, first 4 columns can be called so-called absolute molar mass approaches, which which still, of course, give you the different values of the molar masses, no matter it called absolute. Yeah, it called absolute just only in terms that is independent, but it doesn't mean the correct value of the molar masses. So how do we then decide which molar mass is correct, which molar mass is not, and which diffusion coefficient is okay and which one is not? Well, we apply this the concept of the hydrodynamic environment. So all of these characteristics we measure, intrinsic viscosity, diffusion, sedimentation, or the Brownian coefficient, they're all related to the same basic macromolecular characteristics, the size and the molar masses. So there must be some interpolation, and this interpolation was found in the form of the hydrodynamic environments, the hydrodynamic environment and the sedimentation parameter. And why it is invariant? Because it was found to be invariant for certain class polymer architectures or conformations, right? And over here you have a distribution map, which so the color map represents all known, up to date, is based on the literature data that can be used to calculate a zero, the hydrodynamic environment, or it was already calculated or stated in the papers regarding the different types of dendritic, hyperbranched, or complete family of branch polymer systems, and we see that an average value is going to be 2.6 plus minus 0.4, which actually is smaller than the theoretical predicted limit for spherical particles. So the tendrimers and the hyperbranched polymer macromolecular show lower. If you assume the error, then of course it is within the error, but still it's rather low. So, and we will use actually this value, to judge whether this value of the molar mass is okay or not, or this value of the diffusion coefficient is okay or not. And what we have then, we have this table, but all the numbers that are marked in yellow then going to be excluded from the further analysis, and all others are probably just summarized, and an average value of those will be used for further calculations and analysis. So what do we have then? And we see that even if you use static light scattering, batch one, still it gives you, for example, for low molar mass sample, those values are of the range, yeah. The best examples we have from the combination of the sedimentation and diffusion coefficients estimated from the dynamic light scattering. Interesting. Okay, and then when we have the molar mass, and then I can compare the molar mass in the double logarithmic scale with the sedimentation, diffusion, intrinsic viscosity, and or the hydrodynamic size in the double logarithmic manner, so-called scaling relationships, yeah. And in our case, they all refer to the textbook values for the hard sphere conformation. So we have a hard sphere conformation. So all these hyperbranched macromolecules behave like a hard spheres, Hard sphere actually means, if you apply this friction ratio concept, it means that the friction ratio must be 1. But we observe the friction ratio not 1, it's much higher than 1.5 in average, or yes. And in this case, we remember that the friction ratio is has related to the shape parameters, but as well it is related to the hydration. And in this case, since we know that we have a rigid spherical information, all this effect should be then related to the hydration. Then we can calculate this hydration in terms of gram of water per gram of macromolecule, and we see really large values because, well, it's in average it's going to be 1.7 gram of water per 1 gram of macromolecules if you compare it to the 0.3 gram of water for proteins, for global proteins. So it's a highly hydrated, globular, very condensed and globular structure. And if you look on the hydrodynamic sizes here as well, you see that the highest sizes we achieved 9 nanometers, but this 9 nanometers has a molar mass of around 1 million. Yeah, this brings us to the contraction, to this contraction effects in comparison to the linear macromolecules, right? If you compare the intrinsic viscosity, or basically you compare the translational friction coefficients, rotational or translational of your branched one to the linear one, so it's a comparison of sizes. In these terms, we see that the highest molar mass, such hyperbranched macromolecules will be approximately 50 to 100 times have volume less than the linear analogs. Then if we calculate the volume or estimate the volume of the macromolecules in terms of, for example, intrinsic viscosity multiplied by the molar mass, which will be the first approximation in relation to the volume, we see that plotted in a double logarithmic manner along the molar mass, we see that even hyperbranched or branched family topologies are really different in the volume. Even if you take if you take this hyperbranched polystyrene or esters or hyperbranched polyester ether amides and so on, they really rather large in volume. They're comparable in volume to the linear analogs, actually. They're comparable, yeah? And you have a wide distribution, while the hyperbranched ones, in this case, are really coincide with the behavior of dendrimers. So they're really like dendrimers, like spherical particles, and they're on the other side much easier to synthesize yes. So this is really interesting. The slope of this dependence, of course, will be related to the reciprocal density of the it's a volume and the reciprocal density of the macromolecular coils in this volume representation. Yeah, the slope, the higher the volume, and this basically brings me to the end of my presentation. I believe I have shown you some interesting results on the investigation of the hyperbranched polyglycerols and polyethylene glycols and using this very basic hydrodynamic approaches, and when you combine them, it is very you end up with a large massive of very important information, and this is the very classical way of how the polymer systems are should be studied. I believe, yeah. And of course, I should of course acknowledge all my colleagues without whom all this work would be possible to perform. And actually, this summarize also 4 different institutions. It is Institute of Macromolecular Compounds, Russia. It's St. Petersburg State University. It's Friedrich Schiller University, Jena, and the Laboratory of Organic and Macromolecular Chemistry, and the Mainz University of Organic Chemistry. So it's yes, and of course I thank you for your attention. I hope I was not too long, because I kind of lost sense of time at some point. If there are some questions, I'm looking forward to answer them.